This will be our last lecture on reasoning under uncertainty. So, in this lecture we will wrap up by studying few extensions of the Bayesian kind of probabilistic analysis, and also studying a few other different kinds of approaches towards reasoning under uncertainty. There are of course in this subject a lot of other literature which we are not going to touch upon. For example, we are not going to touch upon reasoning which extends over time, like temporal reasoning, and things like Markov models, etc., or Markov chains, which are used for reasoning with uncertainty over times or over many successive time steps. So, what we are going to do here is going to study a few things which are closely related to Bayes kinds of inferencing. So, the first thing that we are going to look at is default reasoning. Now, default reasoning is a paradigm where we make some default assumptions about some facts, right. For example, if you see a car and you can see two wheels from this side, then by default you can infer that there are two other wheels on the other side, right. So, we make such default assumptions and add them into the knowledge base, right. But of course, we do know that the default reasoning that we are applying here may later on get retracted, because we might find that one of the tires is stolen, right. So, in such cases we find that default reasoning is a kind of non-monotonic reasoning. Now, remember how we had defined non-monotonic reasoning. Non-monotonic reasoning is a kind of reasoning where you derive facts at some point of time which can later on be retracted. So, the other as compared to monotonic reasoning, where whenever we derive something, then that is true throughout the history of time, right. But in non-monotonic reasoning, what is true now or what we believe to be true now can later on become untrue, right. So, default reasoning is where some conclusions are made by default unless a counter evidence is obtained. It is a kind of non-monotonic reasoning. Now, whenever we go for non-monotonic reasoning, the points to ponder are that what are the semantic status of default rules, in the sense that default rules are not always applicable, right, because if you have evidence to the contrary, then you cannot apply the default rule. If you know that one tire is stolen, then you cannot apply the default rule to infer that there are two other tires on that side. Then what happens when the evidence matches the premises of two default rules with conflicting conclusions? So, I can have two default rules with conflicting conclusions, and I have evidence which matches both of the rules, right. So, we have to decide what to do on those kinds of cases. And most importantly, if a belief is retracted later, then how can a system keep track of which conclusions need to be retracted as a consequence? Because when we add a fact into the knowledge base, we can use that fact to deduce other facts. So, when something gets retracted, then all those other side effects will have to be also retracted, right. So, there are things called truth maintenance systems inside such diagnostic systems, which keep track of what is derived from what, and if something gets retracted, then it follows those links to retract out the other things. Okay. Now, one of the most classical means of reasoning is called rule based reasoning. So, modus ponens, for example, is one kind of rule based reasoning, where we deduce, we have certain rules, we have certain facts in the knowledge base, we apply those rules and deduce new facts, right. Now, there was a lot of research done to find out whether probabilistic analysis could be extended to rule based reasoning. So, the rule based reasoning that we have studied in the context of propositional logic and first order logic, in those the rules were certainties, in the sense that if the precondition of the rule matched, then the post condition of the rule is always true. There is no probability associated with that, right. But when we move into the probabilistic reasoning domain, then associated with the rule also you can have a probability. So, you can say that if A and B, then with certain probability we have C, right. So, this was the extension that people tried to think, and then people wanted to see whether the kind of reasoning that we were doing in first order logic could also be extended to the probabilistic domain. So, the basic idea is like this. So, we have that if A and B, then let us say with 0.9 certainty we have C, right. Now, we can have A in our knowledge base, but remember that because we are dealing with a probabilistic situation. So, we could have A with 0.5 probability, right, and we may have B with say 0.2 probability, and then we want to deduce that with what probability can we have C, right. So, one way to infer is that I find out what is the probability of A and B, that is 0.5 into 0.2. So, that is the probability with which the precondition is satisfied, times 0.9 gives me the probability of C, right. Now, this seemed to be very attractive, but it ran into quite a few different kinds of problems. So, we will just briefly see that what are the kinds of problems that will crop up when we try to use this kind of reasoning over the probabilistic domain. Okay. So, issues in rule based methods for uncertain reasoning. Now, these are the problems that I am highlighting out. First problem is the problem of locality. In logical reasoning systems, if we have A implies B, then we can conclude B given evidence A without worrying about any other rules. But we will see that in probabilistic systems, we need to consider all available evidence. It is not just the evidence A that is going to determine the probability of B. There can be other evidence also which can influence it. The reason is that see there is no certainty with respect to A and with respect to the implication, right. So, it is not 100% certain. Then I will give examples for this. Then we have the problem of detachment. So, once a logical proof is found for proposition B, I am referring to that A implies B. Once a logical proof is found for proposition B, we can use it regardless of how it was derived, right. So, if we have A implies B and then somehow we have been able to deduce B, then we do not care how we deduce B, we can just use the fact B in other rules for further deduction, right. But in probabilistic reasoning, the source of the evidence is important for subsequent reasoning. Again, I will explain that why this is so. We will see cases where we have to remember that what was the source of the evidence which led to the deduction of a particular fact. The third thing is truth functionality. In logic, the truth of complex sentences can be computed from the truth of the components. So, if you have A and B or C, then given A, B and C, you can compute the truth of this Boolean formula, right. So, it says that the truth of a complex sentence, which means a first order or Boolean formula, can be computed given the truth of the components. Probability combination does not work this way. except under strong independence assumptions. If you have them to be independent, then you can have the probability of A and B as probability of A times probability of B, otherwise not. So, when we said here that that the probability of A is 0.5 and probability of B is 0.2. So, we can just take 0.5 into 0.2 into 0.9, that was under the assumption that these two are independent, but if they are not independent, then the probability of A and B cannot be computed so easily, right. So, let us start by looking at some of these issues. So, the first issue that we are going to look at is the last one, the truth functionality. So, suppose we have two events H1 and H2, and okay. So, let us say that I toss a coin 2 times, okay, and H1 is the event that we have head in the first toss, right. H2 is heads in the second toss, and T1 is tails in the first toss, right. So, can we write down the, assuming that the coin is unbiased. So, probability of H1 is 0.5, right. Probability of H2 is 0.5. Probability of T1 is 0.5, right. Now, let us look at the probabilities of a few compound events. That if we look at the probability of heads, right. Now, see these 3 events, these 3 probabilities are all 0.5, right. Now, ideally we would like to do a reasoning where the disjunction of any of these gives me the same probability, right, but that will hold only if these are independent events, right. Otherwise, for example, if you look at probability of head 1 or tail 1, this is 1, right. Probability of head 1 or head 2 is 1 minus 0.5 into 0.5, right. So, that gives me okay. So, this is problem number 1. Problem number 1 is that we cannot simply take each of the facts and then deduce the probability of any conjunction or disjunction of those events by a simple formula. We have to know that which of these events are the complements of the other. For example, here the information which was lacking is that H1 and T1 are actually complements of each other, and which in a deductive system you have to explicitly specify, because unless you specify that, how is a reasoning system going to know that if you toss a coin you can have only 2 outcomes, either head or tail, and that the coin cannot stand like this, right. So, unless you specify that explicitly, the reasoning system will not know. So, the problem that we are arriving at here is that for every event that we have, if a set of events together form the universe, in the sense that there is no other possible outcome, then we have to be able to specify that. Otherwise, we will end up in peculiar kinds of problems. Okay. Let us look at another case. You recall that we had an example where we had cloudy as an event, right. Then we had rain, we had wet grass, sorry, this was sprinkler, right. Now, we can always, in a reasoning system, we can put in rules like rain, right. So, if rain, then wet grass, and we can associate some probability with this, some probability say P1 with this. We can also have wet grass this says that if we find wet grass, then most probably it had rained, right. Now, see, if you have both of these rules in the knowledge base, then we have a problem. The problem is that when you have rain, right, that is going to strengthen the probability of wet grass, that is going to, because that is increased evidence that we will have wet grass, right. And then the reasoning system can use that increased evidence on wet grass to again increase the evidence of rain, because if you have more evidence that we have wet grass, then you have more evidence that there is rain, and we are going to go round in circles, strengthening the evidence of having rain and wet grass, right. Now, that is very strange, because that should not happen. So, therefore, the reasoning system should be able to deduce that because I deduced wet grass from rain, so I should not strengthen rain based on the evidence of wet grass, or in other words, it should detect this cycle. And this is typically the case because we have put two rules, one is on the causal inferencing and the other is a diagnostic rule, right. One is from the cause to the effect and the other is from the effect to the cause, right. We can have, typically we can have rules of both types, one is diagnostic and the other is causal, right. So, now, but we have to be careful that this cycle does not take place, and even if there is such a cycle, then the reasoning system should not go around that cycle, and that is why we were saying that it is also important to remember that how we deduced a certain thing. Okay. There can be more peculiar things. Suppose we can have sprinkler with a certain probability P3 to wet grass, right. So, if we turn on the sprinkler, then with certain probability we will have wet grass. The probability can come for facts like there is no water. So, if there is no water, then you will still not have wet grass. So, the probability that there is water is what determines the probability of this rule. And then we can also have wet grass with some P4 or P2. We had this rule already, rain. Now, look at the funny thing that is going to happen. If we have evidence that the sprinkler was turned on, then that is going to increase the evidence on wet grass, right. And if you have evidence that you have wet grass, that is going to increase the evidence that you have rain. Now, by turning on the sprinkler, we are actually increasing the probability of rain. Now, that is ridiculous, right. By turning on the sprinkler, you will end up finding more evidence that there was rain. Actually, it should be the other way around, because you know that the sprinkler was turned on. So, the fact that you have wet grass is explained by the sprinkler being turned on. So, the evidence of rain should actually go down. You should have less evidence that there was rain, because the fact that the grass is wet is explained by the fact that we had the sprinkler on, right. So, therefore, this is another problem, right. So, it is not always that the probabilities should enhance the evidence of the conclusion of the rule. Yes.
In the previous slide, how does sky being cloudy and the sprinkler related? So we have arrows on both sides.
Here? Yes.
How are cloudy and sprinkler related?
Okay, if you find it's cloudy, you are less likely to turn on the sprinkler, because you will anticipate rain.
So both are actually from the individual line.
No. The sprinkler can be an automated sprinkler, which on sensing the sun at regular intervals of time sets off the sprinkler, right. But if it is cloudy, then that device which sets off the sprinkler may not go on. Clear? So, there is a probability, this probability of the sprinkler being turned on depends on whether it is cloudy or not. Okay. But what certainly should not affect is that if the sprinkler gets turned on, then there is absolutely no reason why it should rain, right. On the contrary, that the evidence of rain should go down, right. The probability of rain should go down.
That will improve automatically because being cloudy is low. So
Right.
from there you have
Right. So, if you used a Bayes network kind of analysis, you would see that if you have evidence of the sprinkler going on, then the probability of rain can go down, right. So, if you do a Bayes network analysis on the network that we had seen previously, then you will have that, right. But in a rule based reasoning, we are not being able to mimic that because of these kinds of problems. Okay. So, these were some of the problems that people came up with rule based reasoning. But in spite of that, there was a point of time when rule based probabilistic deduction systems became very popular, and there are at least two very well known tools which became quite popular. One of them is called the prospector. This was a tool which was used for basically geological explorations to find out whether there is some kind of mineral or this thing. So, this was a rule based system which had rules, and you could feed in the evidence and then deduce that what is the probability with which you have a certain kind of mineral or oil or whatever. Right. Another thing, another tool which became very famous was called MySyn. This is a diagnostic tool for pathological kind of inferencing. So, the inputs, this MySyn tool had rules which had associated certainty factors. So, you have if you have evidence of A1 and B1 and so on, and then you can deduce with certain probability say 0.7 or so some C, right, some conclusion. So, the rules were of this form, and in MySyn specifically the attempt was to keep all the rules of one type. So, if you keep all the rules to be either causal or diagnostic, then the problem of those kinds of cycles do not come up, right. Moreover, you try to keep the rules always so that the evidence so that the conclusions are non-conflicting in nature, so that you do not have problems like sprinkler to wet grass and wet grass to rain, right. So, you are not able to deduce something which is conflicting with what you have. So, this careful structuring of the rules actually helped in this being successful, right. So, later on also there has been several other rule based systems, diagnostic and information systems, which use probabilistic reasoning, but they are all very carefully designed to avoid such kinds of problems, right. A different school of thought came up with an idea which was quite revolutionary at that time. They said that besides the probability, there is also a thing called belief. What is important is the belief of a person when doing an inferencing. So, instead of modeling the probability, they thought about modeling the belief. I will explain through an example that what is this change. Okay. So, we will briefly study a theory called Dempster-Shafer theory. So, this is designed to deal with the distinction between uncertainty and ignorance. Right. We use a belief function called BELX, which represents the probability that the evidence supports the proposition, right. So, it is something like the kind of rules that we were saying, that it is with what probability does the evidence support the conclusion, right. When we do not have any evidence about x, we assign belief x to be 0 as well as belief of not x to be 0, right. So, now let me give you an example, that suppose this is an example which I have picked up from Norvig and Russell. The example goes like this, that suppose some person comes to you with a coin, right, and says that if you toss the coin, then you are more likely to get head, right. Now, you do not believe that character, but that character says that if you toss the coin, you will get heads 90% of the time, right. Now, because you do not believe that person, so if x is the event that you get heads, then I will say that my belief that we will have x is 0, because I do not have any evidence to support the fact that x will be heads. Likewise, I do not have any evidence to support that it will not be heads either. So, belief of not x is also 0, right. Now, suppose a very reliable person comes and tells us that with 90% probability the coin is fair. So, a reliable person comes to me and says that I am 90% certain that this coin is fair, right. So, then I will say that belief that it will be heads is 0.5 into 0.9. 90% certainty of the rule and 0.5 is the probability that I have heads, because he is saying it is fair. So, the probability of heads, if it is fair, is 0.5. So, this gives me 0.45.
What if it's fixed? If it's fixed, also you can have fixed in that case also.
If it is,
If the coin is fixed, you can also have fixed.
if the coin is fake, I do not know whether it is fake or not, I do not know. So, I am just going by the evidence that I receive, right. So, the whole idea is that how can I use the evidence and the belief of that evidence to deduce my belief of the conclusion, right. So, my confidence in that person is 90%. So, I have this 0.9 and that person says that the coin is fair. So, if the coin is fair, then the probability of head is 0.5. Previously it was 0 because I had no idea whether the coin was fair or not. I did not have any evidence that the coin was fair. So, my belief that it would be heads is 0 and the belief that it would be tails was also 0. But now that this person on whom I have 90% confidence comes and tells me that it is fair with 0.5 probability. So, I conclude that it is 0.45, right. That is my belief that it will be heads. And what is my belief that it will be tails? .5 again for the tail and 0.9 because I again that confidence in that person. So, I have 0.45 again, right. Now, see that the gap between the belief of x and not x is still not 1, right, and how much gap do I have between the two? 0.1. What is this 0.1 accounting for? This 0.1 is accounting for my lack of confidence on the person who is saying. So, I am not 100% certain about the evidence, I am only 90% certain, I have 90% confidence in that person who is telling me that the coin is fair, right. If I had been 100% certain, then the sum of these two beliefs would have given me 1, right. So, this was the basic idea around which Dempster-Shafer theory was built, right. So, this is that example only. If we are given that the coin is fair with 90% certainty, then we have 0.45 and 0.45 and we still have a gap of 0.1, right. Okay. So, this was a paradigm shift from probability to belief, but this theory did not really pick up very much because mainly because it was not very clear how to include this kind of belief inside a rule based system, and also the actual meaning of this belief and how we should interpret that in deducing conclusions was not well understood, right. So, it's more because of the lack of people's understanding and what should I say, and the belief on the theory that led to the almost obsolescence of the Dempster-Shafer theory, right. But we do have one kind of theory which has come up in a big way, right. But again, I have personally quite a bit of reservations about this theory also, but nevertheless let us just get a flavor of what this theory is about. So, fuzzy logic. Now, fuzzy logic makes again a paradigm shift from probability to possibility, right. So, again we do not talk about the probability of an event, but we talk about the degree of truth of an event, right. So, as I had given an example previously, then that if we have a person and we want to find out the probability that he is fat, right, then we say that fatness is a Boolean, that he is either fat or he is not fat, and then we talk about the probability that x or y is fat, right. But when we talk about fuzzy logic, we say that no, fat is not a Boolean, it is a set which has fuzzy contours. So, at some part in the set, for some members, well, they are definitely fat. For some members, well, they are fuzzy. So, fatness is actually a graded truth, right. So, how fat? Now, depending on how fat, we can have other kinds of things, like for example, suppose we want to make a rule based system that if a person is fat, then he is more likely to have a cardiac problem, right. Now, given that x is fat, now then it depends on how fat. If he is very fat, then he has more chance of having a cardiac problem. If he is less fat, then he has less chance of having the problem. If he is not fat at all, then he has negligible chance of this thing. So, again the outcome of whether he has a cardiac problem or not, or the likeliness or the possibility of that person having a cardiac problem depends on how fat he is, right. So, in this logic we deal with fuzzy set theory, which is a means of specifying how well an object satisfies a vague description. Truth is a value between 0 and 1. Uncertainty stems from lack of evidence, but given the dimensions of a man, concluding whether he is fat has no uncertainty involved, but it has fuzziness involved, right. So, if you know the person, if you have the dimensions of the person, then there is no uncertainty about that person's being fat or not. It is only about how fat we are going to rate him, right. Then the rules for evaluating the fuzzy truth of a complex sentence are as follows. When we have two events A and B, then the truth of A and B is the minimum of the truths of A and the truths of B, right. So, if A is fat and B is slow, then the truth that a person is fat and slow is given by the minimum of how fat he is and how slow he is, right. Now, we can debate for hours about the choice of the mean function for this. People found was, okay, I will come back to that. Let us first see the other rules. if you have A or B, then it is the maximum of the two. So, you see here we are not looking at anything like conditionality or anything, there is no such thing, because there is no uncertainty involved here. It is just the degree of truth that we are talking about, right. So, there is no conditionals or anything like that, and we just deal with the min and max operators. So, the analysis itself becomes much simpler than that of Bayes networks, right. And the truth of not A is equal to 1 minus the truth of A, right. So, these are the three basic rules for analysis on fuzzy sets, right. Every event A, B, C, whatever, they are all sets, right. For example, fat is a set. If you define the continuum of weights of all persons of the world, then a subset of that is fat, right. Tall is another subset, right. So, these are all sets, and we are working on these sets only. So, it is a kind of set theoretic operation, except that we associate a truth with the set, and perform all the deductions based on these min max and complement operators, right. So, people did find that this kind of analysis was simplifying things a lot, and they found also that in those kinds of simple situations where you do not have too much of dependence between events, the kind of deduction that you do with fuzzy logic approximates what you would do with a comprehensive Bayes analysis, right. So, people found that there is actually an approximation of the Bayes analysis that you do obtain through fuzzy analysis. But in cases where the system is large, you have many events and there is lot of interdependencies, this has failed also miserably, right. So, it is not good for everything. Also, it has been used to some extent in different kinds of control systems, particularly in the kinds of control systems where you have continuous variables and you want to specify the gradation of control through a fuzzy set. So, you want to say that if the blast furnace becomes very hot, then do this. If the blast furnace is somewhat hot, then you do this. So, that hot is a fuzzy set, and different rules that you want to apply on controlling the blast furnace can be specified in terms of fuzzy rules, right. And the degree of control exercised by all these different controlling mechanisms are also graded depending on the value of the hot or the truth of the hot, how hot, right. So, the critics of fuzzy logic believe that the same kind of control could also be achieved if you just perform the simple discretization of the continuous system and then you use normal reasoning, right. And people think that it is more because of the sophistication in the control system itself that led to the success of fuzzy controlled things. You know, you have fuzzy controlled washing machines and things like that being advertised. So, the critics of fuzzy logic believe that it is more because of the design of the systems that they are successful rather than the success of the logic which is driving this, and that more simpler logic which just discretizes the system and performs elementary reasoning would have done just as well. But it is still open to debate. Fuzzy logic is still part of research, and well, in future we will know that whether this is really very useful or not. Okay. So, with that, yes.
In fuzzy logic, T of A and not A.
Yes.
But it will never be 0 unless T of A is 0, because it is minimum of T of A and not A.
Yes, yes, yes. You have problems like that in fuzzy logic as well. right?
That means formula can't be true.
Which formula?
First one,
The third one?
first one. Suppose T of A is 0.1
Yes.
and suppose B is not A. So T of A and not A will be 0.1.
T of A and T of not A. Yes.
0.1.
Yes.
It should be 0.
No. No. See, that's what is the meaning of a fuzzy set. See, in the border areas, the truth and its negation both can have certain values. It's not going to be 0. You see, it's not a Boolean that you are talking about. It's not a Boolean. So it's not that if it is A, then it is not A. It can be, a person can be fat and he can also be not fat, because you are in the fuzzy region, right. So that's why we have this anomaly. Okay. So with this we come to the end of the chapter on reasoning under uncertainty, and the next topic and possibly the last topic that we will pick up is on learning, on machine learning.
1951. A young nation aspiring to find ways to fulfill a dream lays the foundation of an institution that will give aspiring technocrats the license to fly high. The first Indian Institute of Technology is born at Kharagpur. Founded on the basis of the recommendations of the N.R. Sarkar Committee that was set up in 1945 to consider the development of higher technical institutions in India, the institute was first established in 5 Esplanade East, Kolkata, before it moved to Kharagpur in 1951. With Sir Gyan Chandra Ghosh as the first director and Dr. B.C. Roy as one of its founding guardians, the institute established itself as the symbol of a young, dynamic and resurgent nation. As top students rubbed shoulders with the most celebrated of professors and scholars, visions took shape. And IIT Kharagpur continued to play the pioneering role that was envisaged for it, enabling India to become a knowledge powerhouse that it is today. At every stage of its evolution, IIT Kharagpur remained ahead of its times. It provided the best of facilities for the budding technologists, helping them shape their own as well as the nation's future. Indeed, today, IIT Kharagpur has blossomed into a time-tested, venerable institute of learning. With the rich experience of converting individuals into brilliant professionals through 50 glorious years. As you cross the campus gate, you feel the distinct nip that is IIT Kharagpur. The spirit of objective inquiry and lateral thinking hangs heavy in the air. The modern township-like campus of IIT Kharagpur, set in sylvan surroundings, is self-sufficient in all respects. From modern banks to the good old post office, from vast playgrounds and well-equipped gyms to modern auditoria and open-air theaters, and from the quiet fiber optic linked residential quarters for the faculty to the web-enabled hostel rooms for the students. At IIT Kharagpur, lush green bowers of tranquility coexist with smart cards and ATMs. Spread over 690 hectares of sprawling cyber habitat, 120 kilometers from Kolkata, IIT Kharagpur is one of the largest network campuses in Asia. Just the academic complexes itself spreads over a built-up area of about 2 million square feet, of which 150,000 square feet is the new complex that commemorates the Golden Jubilee celebrations. And that's not all. It is the only IIT to have conquered territory beyond its own through cutting-edge courses offered in its extension campuses at Kolkata and Bhubaneswar. IIT Kharagpur is not just about its large campus, but its diverse range of activities. It offers the widest spectrum of disciplines, ranging from aerospace, biotechnology, cryogenics, to architecture, mining and agricultural engineering, supported by strong faculties of sciences, humanities and management. There are more than 30 departments and centers that offer the largest number of undergraduate and postgraduate courses amongst the IITs. The courses are ever evolving and show the way for other sister institutions. The richness in its diverse activities is showcased by the technological support the institution provides in areas like architecture, agriculture, post-harvest technology and medical sciences. The institute has revolutionized and popularized rice milling technology. The other major contributions of IIT Kharagpur have been in the critical fields of defense, railways, space research, power systems and petrochemicals. All these activities directly empower the human requirements of the nation. Advanced facilities at the Institute make it possible to undertake cutting-edge research and service-sponsored research projects. The array of equipment ranges from aerodynamic testing laboratories to intelligent machining centers, atomic spectrometers, to VLSI design labs, molecular beam epitaxy, to anechoic chamber, fast protein liquid chromatographs, to liquid nitrogen plants. The cutting-edge technologies are at par with the best research facilities across the globe. In fact, the volume of research and development activities at the Institute is incredible. In terms of the number of patents it owns, the volume of industrial consultancy it provides, and the revenue that it earns from all these make IIT Kharagpur a class apart and strengthens its position as the true pioneer in technological education in India. The Institute Library deserves a special mention. Fully web-enabled, it is one of the largest in Asia with over 324,000 volumes of material, including books, videos, microfilm, and patent documents. champions that ensure a student's mind develops at the right pace. Along with its strong sense of academics, which is ensured by a strict selection process, life at Kharagpur is a celebration of, well, life. And at its heart are the students. In fact, the saying goes that you can take an IITN out of KGP, but not KGP out of an IITN. You've left a part of you behind. For most of the students, life in the campus was in itself a festivity, a collage of activities that shaped their mind and body, a collage of events that was a synthesis of competition and cooperation, a collage of interests as diverse as dramatics and ham radio. Yes, life at Kharagpur has always been exciting. And the years cemented lifelong bonds as lives mingled over cups of joy and stretched over stimulating semesters. The halls, with their blocks and wings connected by charming catwalks, remain ensconced in their own world. A collage of memories. Infrastructurally adequate, architecturally meticulous, and holistically inspiring, where students, wherever they might be from, invariably come into their own, developing their individual talents, honing their skills to take on challenges with confidence, so they can move ahead in fulfilling their dreams. What makes IIT Kharagpur so unique is its environment. Undiluted by the diversions of metropolitan surroundings, the close-knit campus life enhances the entrepreneurial and innovative spirit of the achievers to be. Indeed, in this golden jubilee year, as the celebration continues, Pandit Nehru would surely have been a proud man today. For him, IIT Kharagpur was always more than just an institute of technology. In his own immortal words, it is indeed